Hi. Thank you guys all so much for coming. I'm Miss Holman. I was Roshan's mentor for his SHIS this year. And I just want to say, like, it's been the most incredible experience. You'll see kind of as he goes through that, like, what he has put together and what he's done, not just this last semester, but like over the last, what, 6, 7 years,
5 years.
has been like absolutely incredible. So I'm not going to spoil it. I'll let him kind of do his thing, but be excited. It's going to be really good.
Hello, everyone. Can everyone hear me in the back too? Okay, good. I just want to get the volume correct. My name's Roshan Taneja. I am a senior here at the Prep, and my SHIS today is on object detection on public satellite data for scaled placement of rainwater harvesting units in East Africa. What a mouthful. I'm sure you can imagine. There's a lot of things going on in this title, so let's start from the very beginning. Approximately, approximately 5 years ago, this picture was taken where my brother and I are in the depths of northern Tanzania. He and I were walking from Boma to Boma, which are Maasai living locations, just observing the culture, being part of the community, but also being part of an initiative that is part of one of the most pressing issues in the world, and that is water. In the Monduli district of Tanzania, where we were located, the Maasai community, approximately 30,000 indigenous people and part of the oldest tribe in the world, rely on water that looks like this for their day-to-day activities. And this is water that's only available during the rainy season, which is about 6 months of the year. The other 6 months of the year, this exact location looks like that. Um, and as you can imagine, in such dire circumstances, people resort to extremely dirty locations that have pathogens or water that is incredibly unsanitary to drink. But because of necessity, that is the only thing that they have. Especially due to how far they are from any city centers or highways, it makes it incredibly difficult for this community to access water on a basis that would allow for their survival. So in 2022, my brother and I, we fundraised and deployed our first rainwater harvesting unit, which you can see right there on the right. It holds 100,000 liters and it harvests water from the roof of this community center that was also built in the same year. We also helped paint it, and as you can see here, it is massively impactful to the community. In fact, the numbers speak for themselves. The unit itself supports about 4,500 Maasai in that community. And based on a field survey that we did that year as well, we identified an increased amount of activity in economic activities, educational activities, because of the reduction in the average time that a lot of the Maasai spend walking for water. In fact, that was almost a 60% reduction from 9 hours a day on average to about 3 hours a day, which is a transformative experience for the Maasai that live in these areas. So I'll give you a second to take a look at that because there's a lot of text on that screen. But what we wanted to do here is, after seeing a lot of the research results and seeing how impactful it is for just such a small community as part of this larger community, we wanted to scale it up. So what we wanted to find is, how can we support all 30,000 Maasai in this area by placing rainwater harvesting units in a manner that is efficient and effective in minimizing the costs and minimizing the amount of time to deployment. The reason why this project was on a time schedule is because the rainy season starts in about December, and I needed to deploy these rainwater harvesting units by the end of November. Otherwise, building them during the rainy season and the monsoons would be incredibly difficult. One of the biggest issues that we had was that there are no government provided maps or populations or census guides that allow me to detect where these populations are. And as a result, we'd have to use satellite imagery to survey the data and identify these best water harvesting unit locations effectively. So some of you might be wondering, what even is satellite imagery? Some of you, maybe. Some of you may be a little bit familiar with it, but satellite images or Earth observation, satellite image photos, if you'd like to be pedantic about it, is a type of Earth observation imagery where images of Earth are collected from orbiting satellites around the Earth. In fact, this is one of the first photos of the Earth ever collected by a satellite. I'd like to coin this moment as the moment humans discovered the Earth. It's a quite beautiful moment if you think about it. Um, Satellite imaging companies sell all kinds of images and license them to governments for applications like Google Maps or Apple Maps, if you're familiar with those. But the technology has advanced a lot further than this very grainy photo of the Pacific Ocean and a lot of space. In fact, a lot of resolution can go up to 44 centimeters on the pixel, which is better than the resolution of my MacBook camera looking at it from 100 feet up, which is incredible. Uh, the increased resolution of these satellites allow for an immense array of technologies. The instruments used, such as infrared technologies, ultraviolet technologies, as well as color sensor data, allows us to identify a plethora of image resolutions and types of features on maps. Here are some of the available services of satellite imagery. I like to break these into the good guys and the bad guys. The reason for that is because these publicly available satellite sources are a godsend for people like me who are trying to do academic research. In fact, the United States under President Biden has led the way in making this data freely available for scientific use. And the European Union's Sentinel constellation, which is a set of satellites across the entire world that orbits the entire world and takes pictures of every square inch on the entire world. It just became public about 6 months before I had to use it, which means the timing was absolutely perfect. You may notice a couple other familiar names here, such as Airbus or Planet, as well as USGS and NASA, which is the United States Geological Survey. So these satellite sources are incredibly useful to us. But what exactly are we using satellites to look for? You may be wondering, okay, we're looking for populations, but how do we know what the populations look like? Well, this is a Maasai living unit. It's called a boma. I may have mentioned it a little bit earlier, but the bomas are a living unit that houses between 10 to 50 people because the Maasai community is actually polygamous, meaning one man, multiple wives, and many, 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 many children. Each one of these bomas is very distinct, and every single one of them is unique in a special way. A couple key features that allow us to identify these are that they have an outer ring, typically made of dead bushes or shrubbery, and an inner ring that's used for holding cow. A more prime example is this one right here, where you can see the outer and inner rings. But because of different features, as well as different materials, as well as the size and location of these, makes them incredibly difficult to identify. Other issues with the satellite data that we could be using are that there's contrast issues, as well as the bomas blending in with the surrounding terrain, and cloud cover. Cloud cover is one of the most notorious issues in satellite data because, as you can imagine, if you're taking a photo from 1,000 feet up, you can't exactly coordinate where the clouds are going to find themselves on your photo. So let's play a little game. I reduced the cloud cover for this one, but there is an image. I want you guys to take a second, maybe speak with your partners and find out exactly how many bomas there are in this image. I think I'm counting down, but remember, they can blend in with their features, and also some features can look like bomas, but not exactly be bomas. Does everyone have a number in mind? Does anyone want to share? Taylor. Okay. Another one. Kelly. 7. 7 is correct. What you guys may be thinking are bomas are either small outcroppings or quarries, such as this one down here. This one's actually just a pile of rocks in the middle of this area. But these locations here, you can see how they're significantly darker, as well as the fact that they're closer bunched together and they have that inner ring and outer ring structure. As you can see, a lot of you may have had higher numbers around 10 to 15, and that is a similar issue that I might get when I'm trying to detect these myself, which is why we can try and use computers. So where are we going to help place these rainwater harvesting units? There's no infrastructure like roads or electricity. In fact, most of the time when we're trying to do population analysis, we use night photography. And the reason for that is because of electricity, we can identify where lights are and identify where general centers or urban centers are because of street lights, because of buildings. But in this case, there's no electricity, there's no water lines, there's nothing in that sort that would allow us to kind of extrapolate from that data to see where the populations are. So where does the population live and how can we find it? Well, I did a little bit of reading. You don't have to look at all of this because this is just the names of the papers, but you can look at that funny little XKCD there that kind of explains that we're using a convolutional neural network. I'm not sure if anyone knows what that is, but I'll explain what that is in a little bit. Essentially, what I want to do is use AI to find where these bomas are by looking at the map, not through my own eyes, but through a computer. So for some of the nerds out there, you can maybe look up some of those papers. I know William was as well. So um, here are a couple techniques that I considered for this image classification task. We have our big three players in the image classification field. I won't bore you with all of the details, but we ended up going with TensorFlow because it's incredibly versatile. In fact, it works in two separate languages, both Python and JavaScript, as well as the fact that it's very easy to set up and it's super beginner friendly in comparison to YOLO v7, which is a lot more of a specialized tool, but it's also very difficult to work with. And OpenCV, which is super customizable and super available, but it's very complex to set up for such a much smaller task like mine. So using that CNN, we decided to create an image processing pipeline. This pipeline will help get from the images of the bomas that we already have to find the locations of all of the bomas that we can find. So it has 4 steps here. This is very overwhelming, so we'll break it down for you. Let's start with the image processing pipeline database. The image database contains just raw data of the images plus the metadata. Each image contains color, which is 3 channels of color, red, green, and blue, as well as infrared data, and each image contains an orientation and location. The location is in the geospatial coordinates, and the orientation is literally just a character that says north, south, east, or west. Simply all of that. The reason for that is because we end up using a little bit of data augmentation in the future, which I'll also get into. For detecting the dwellings, there's a little bit of black box magic here. In fact, this TensorFlow model, you could essentially identify like this. Some people will get past this point, and it's a totally fine to understand it as a black box. You throw in a lot of data, you stir around the linear algebra and the numbers, and then sometimes a little stuff comes out and it looks right, maybe. I don't know. Is that 90% likely a BOMA? Pretty much looks like one to me. Well, under the hood, it's a little more interesting. We have a couple different layers here. We'll identify 4, as well as some of the layers that we've taken out in the middle of the process of aren't super interesting or super technical to the specific area. But let's go down the list here. So resizing layers. Resizing layers essentially adjust the input, which is specifically just the image, and to an image size that's compatible with the CNN. For us here, we have 100 by 100 by 3 channel color image. And because of that, that's a lot of pixels. In fact, if you want to do the math, it's 30,000 pixels or something along those lines, because of each channel having its own pixel color data. The convolution layers are maybe the more interesting parts of this. They use something called a filter, and they pass over the image and extract key features of it. This can be an edge detection filter, which detects edges in a photo like this. Or, for example, an edge detection filter can identify like the bridge of your nose or your eyes for the Face ID on your phone. In a similar manner, we can use several convolutions in a chain to identify key parts of what we're trying to filter out. In this case, the first few convolutions are typically edge detection. And then along from there, we can focus on things like ring-based structure or other types of filters in the area, which is quite a nice tool once you think about how it can generalize larger concepts into smaller, more quantifiable pieces of data. In addition to that, we also used some data augmentation. Oop, on the wrong side. Yeah. So this is one photo of a BOMA. And when we had 2,000 handpicked photos of BOMAs, our model accuracy, especially our validation accuracy, was incredibly poor. Now, there's a couple reasons for this. The reason one is 2,000 photos is not a lot. You'll see in a second 2,000 photos is really not a lot, especially when you're using part of your images to train and part of your images to test whether or not your model is good. What we ended up doing was rotating each image independently to 4 times our data set. And that ended up actually having a spectacular advantage on the accuracy of our model. The key insight here is we can get more data from rotating our images. And as a result of that, it makes our model that much more accurate because it's able to generalize these features in all directions. It shows that models, the BOMAs are not necessarily orientation specific, they're more orientation agnostic, and the orientation and position of them in an image is not particularly useful. Um, so that's how our model training and process works. But how exactly does the model work in practice? Well, that's the third part of our pipeline here, specifically in my favorite application in the world, Google Earth Engine. Now, I had so many issues working with Google Earth Engine through this SHIS. I'm not going to get into them, but I'll have you know if you ever want to use Google Earth Engine, you should contact me first, or you will lose a lot of money because it is very expensive. So essentially what we do here is, as you can see, the BOMA model, the BOMA detector model is ported into Google Earth Engine. And as I said earlier, because of its compatibility with Python and JavaScript, and Google Earth Engine's main focus on being a JavaScript querying kind of language, it's based on JavaScript, but it's difficult to kind of understand the syntax of. It can run that model inside of Google Earth Engine, which is also very expensive, and I don't recommend doing that. But what I can do here in Google Earth Engine is I can actually query a location and get the actual live satellite data from that location last week, 2 weeks ago, 6 hours ago. It depends on how often the satellite has traversed over that area. But what we can do here is say, hey, Google Earth Engine, can I see what Monduli, Tanzania looked like maybe a week ago? Sure. Why is it bright red? I know all of you are wondering why it's bright red. But in addition to that, you can see some other key features on the map. And that blue trapezoid there is water. Everything red here is actually land. And this kind of further heightens the contrast of how much water there really is on a per land basis. There's 2 lakes here in this 250 square mile area. In fact, the deepest that lake gets is about 8 feet. So there's really not a lot of water here. The reason it's red, I'll get back to that. No, I'm not. It's an infrared data map. The reason it's infrared is because the BOMAs reflect a lot more information from their dead shrubbery and dead bushes, because the dead shrubbery and dead bushes reflect infrared light more than the ground and the living trees and things like that, which makes it extremely easier to identify where these BOMAs are. In addition to that, this image is absolutely massive. Because of its extremely high resolution, this image is about 530,000 pixels by about 280,000 pixels, which takes it close to 50 gigabytes on my computer when I download it. And my computer is not that strong, so it is really chugging as it's starting to download this massive image. In fact, it's bigger than most of the video games I have on my computer, which is crazy. But running the model in Google Earth Engine was a completely streamlined process. In fact, there's a lot of libraries out there that allow you to run models on there of all different kinds, from random forest classifiers to CNNs. If you know what I'm talking about, it's a pretty interesting process. Running the model on here outputs something that looks like this. Ain't that lovely? It's a pretty nice map. It's a pretty cool points, but you really can't see it in relation to the map. So using Google Earth Engine's built-in point placing, we can get something that looks like that. That is 488 locations detected on one screen. That is 488 communities of 10 to 50 people in one location on one screen. And we can see a couple key features here. If we use a clustering algorithm, we can identify small communities. Clustering algorithms are an algorithm that allows you to group points together. It's used in all kinds of technology, from ChatGPT, from grouping words that are vectorized together, to different types of decision-making algorithms. even Blackjack uses some clustering algorithms as well for Blackjack bots that you may use in online gambling and things like that. So it's a fairly universal experience. And for some reason, it somehow seems to work here. Because when I use the clustering algorithm, I also changed it so you're not staring at a red screen all the time. But you get something that looks like this. These are the communities in groups that seem to be holding together in small areas. And we can identify some key features here, such as the fact that groups C, E, D, H, and I live along large geological formations like dried riverbeds and small highways, as well as G, J, and K, which live along the highway because of water trucks that pass by, and smaller communities and pipelines that may live alongside the highway. That white X that you see in the middle here, I'll just point to it so you can see it. That's actually where our first rainwater harvesting unit was placed. So this is a pretty spread out community. In fact, the average distance between each of these is close to a mile or two, which takes quite a bit to walk, especially if you need to walk from, let's say here, all the way to that rainwater harvesting unit. That can take several hours. So how exactly are we going to place these rainwater harvesting units to help a large expanse of this community? Well, we're going to use this water harvesting unit placement area in our pipeline here, obviously. Well, what does that mean? That means that we're going to optimize the placement of these locations. Now, that comes through a series of both human evaluations as well as identifying the distance from the bomas to the closest locations of water. And that leaves us with three communities that are in pretty extensive need of aid, and that is communities A, B, and F. And that's where we'll be focusing most of our efforts on deploying the rainwater harvesting units, especially in the upcoming rainy season. We need them to be deployed there first because of their distance from the highways and their distance from nearby rainwater harvesting units. So there's a couple problems to address with this model. I'm sure you may believe, oh, wow, what a great model. It detected everything perfectly. Well, the whole process of this is based on uncertainty. In fact, when the model only reaches about an 80% level of certainty is when I drop a pin on the map. And so when you come here and you're thinking, hey, is that really one BOMA detected? You really can't tell from the imagery that you're looking at. But this is the exact same imagery that you guys were looking at. In fact, it did pretty well. It missed 1 point up here, but all in all, it actually got most of those points pretty down. So it did seem to do pretty well. There's a couple issues with the model, though, that I needed to kind of iron out before coming up with that final solution. And the fact is that the model seems to struggle with BOMAs that blend in with the environment, as well as when there's small overlaps when scanning. And the reason for that is, let's say you have a BOMA and then your image basically comes over and scans over like half of the BOMA the first time and then half of the BOMA the second time. It would never end up classifying either one of those images. Or if it ends up with two BOMAs in one image and it classifies it as one. So that can have issues with our population count, as well as the fact that our not BOMA data and our BOMA data were unevenly classified data sets that we trained our model on. So those are a couple limitations that you should keep in mind when you're thinking about technologies like these, as well as the fact that not all of these technologies can be ultimately relied on to make a decision, and sometimes some human decision making needs to be made as well. So what exactly was the outcome of this project? What exactly did we end up doing here? Well, those 488 points allowed us to place 108 rainwater harvesting units benefiting close to 10,000 Maasai before the end of November. Now that's an immeasurable feat that I couldn't have done without several people on my on the side of the Tanzanian in Tanzania working on ground. In fact, there were nearly a dozen engineers and several community leaders who were behind this project. But the data that I provided them that allowed them to detect where their locations of their communities were was invaluable. It helped them essentially decide where to place these water harvesting units first. In fact, this data and this project was a pretty impactful project. My brother and I were able to present at NeurIPS in December, right after the rainwater harvesting unit project was completed. And that was a pretty interesting process as well. So I'd like to thank everyone who's been a part of this project. it's been an immense pleasure of mine to be able to do this, a massive community, and really learn a couple things from that. So that is my thank you. I'd like to personally thank a couple people. Uh, Mr. Ramos, first and foremost, for setting up this SHIS program. I really appreciate it. I know he isn't here right now, but he's with us in spirit. Um, Miss Holman for being a mentor. She's been invaluable, not only in the researching process, but the identifying of key algorithms, the identifying of some of the most key parts of my project that I want to be able to present to you guys, as well as just being a great friend and mentor. So thank you very much. I'd also like to thank my off-campus mentors, Miss Rachel Portelli, Professor Alp Kuchik-Helbier, CC Wang, and Ananya Rao, who's a PhD student at Carnegie Mellon. So she really deserves my thanks because she was also very helpful for this. And I'd like to lastly thank my brother. He did a lot of the manual classification and labeling for this. I really made him do a lot of the grunt work for this project, and completely unpaid too. So props to him. And I will leave you there. Thank you guys so much. Is there anything I can answer? Any questions at all?
Applause first.
Let me just stop the recording real quick.